Most people picture the edge of the universe as a wall, a final surface, some kind of cosmic finish line where space just stops and something else begins. I used to picture it that way too. The problem is, the more you actually dig into the physics, the more that picture falls apart in your hands. There is no wall. There are 4 different edges, hiding at 4 different distances, and every single one of them turns out to be a horizon in disguise. Not a place, a condition, a line drawn by your relationship with the rest of the cosmos. So settle in, hit that subscribe button, and stay with me through this one, because by the end, you're going to realize the edge has been wrapped around you the whole time. Part 1. The question that breaks itself. There are galaxies you can see tonight, right now, with the most powerful telescopes humanity has ever built, that no signal we send today will ever reach. Not in 1,000 years, not in 1 billion, not ever. Their light is still arriving at our detectors, photons that left those galaxies billions of years ago, still streaming into our instruments like letters from a friend who has already moved beyond any address we could write to. We can watch them, we just cannot touch them. And every second that passes, more of them slip across that invisible line, joining the silent majority of the universe that exists in our sky, but no longer exists in our future. That sentence should bother you. It bothered me the first time I really sat with it. Because the moment you understand what it actually means, the entire question of where the edge of the universe is, the question that has probably haunted you since you were a kid lying on your back in the grass, trying to imagine what came after the last star, that question stops making sense in the way you thought it did. It does not get answered, it does not get solved, it dissolves. And what replaces it is something stranger and far more personal than a wall at the end of space. When most of us picture the edge of the universe, we picture something almost cartoonish. A boundary, a surface, a place where you could press your hand against the inside of a celestial dome and feel the resistance of whatever is on the other side. Maybe a wall of fire, maybe a sheet of nothing, maybe a sudden silence where atoms refuse to exist. The mind wants a finish line because every other journey we have ever taken has had one. You drive long enough, you hit the ocean. You sail long enough, you hit another continent. You climb long enough, you hit the summit. So when we ask about the universe, the brain insists on the same logic. Travel far enough, and surely something stops you. The problem is that cosmology, the actual science of the universe at its largest scales, refuses to give us that answer. It does not give us one edge. It gives us several. They sit at different distances. They obey different physics, and they contradict each other in ways that should not, mathematically, be possible to reconcile, except they are. The universe is wearing 4 different masks, and behind each one is a different definition of what an edge even is. There is the edge of what we can see, sitting at roughly 46.5 billion light-years away in every direction. There is the edge of what we can ever reach, sitting closer at about 16.5 billion light-years, and that one is moving toward us, not away. There is the question of the universe's underlying shape, whether it is flat and infinite, or curved and finite, or wrapped around itself like a cosmic donut. And then, on the speculative frontier, there is the possibility that our entire universe is a bubble inside a larger structure, with a wall somewhere out there separating our physics from physics that might not even be recognizable as physics at all. I want you to hold all 4 of those in your mind for a moment, because we are going to spend the next several hours pulling each one apart, and the journey through them will not be linear. It will spiral. Each edge we examine will turn out to dissolve into something else, and by the time we reach the last one, the question itself will have changed. We will not be asking where the edge is anymore. We will be asking who the edge is around. Here is the central paradox, the one I want you to carry with you the whole way through. We can see farther than we can ever reach. visibility, and interaction are not the same thing. The light from a distant galaxy arriving in our telescopes tonight is a fossil, a frozen message from a place that was once close enough to communicate with, but is now, because of the way space itself is stretching, drifting beyond the range of any reply we could ever send. The universe lets us watch what we cannot touch. That is not a limitation of our technology. That is not a problem we can solve with bigger rockets or faster engines or smarter physics. That is built into the structure of space-time itself. The numbers come from the Planck satellite, the most precise measurements of the cosmos we have ever made, finalized in 2018 and refined since. The observable universe stretches out about 46.5 billion light-years in radius. That is the distance to the farthest objects whose light has had time to reach us since the universe began. The cosmic event horizon, which is the boundary beyond which nothing we do today will ever influence anything out there, sits at about 16.5 billion light-years. And that horizon is shrinking in proper distance, year by year, decade by decade, because dark energy is causing the expansion of space to accelerate, and the faster space expands, the smaller the region we can ever causally affect. Let that sink in. The pocket of the universe you can ever reach is getting smaller, not because anything is moving, because the rules of the game are changing under your feet. And every galaxy that crosses that horizon tonight, while you are watching this, becomes permanently, mathematically, physically unreachable. Their light will keep arriving for a long time, slowly redshifting, slowly fading, but you cannot send anything back. You cannot wave hello. You cannot even, in principle, be informed of anything that happens to them after the moment they crossed. This is not a technological limit. I want to keep saying this, because the brain wants to argue with it. The brain wants to say, well, give it time. Eventually, we will figure out a way. We figured out flight. We figured out the moon. We figured out splitting the atom. Surely we figure this out too. But this is not that kind of problem. This is not a wall we have not yet learned to climb. This is the geometry of the universe itself, drawing a line and saying, nothing on this side ever interacts with anything on that side again. Not light, not matter, not information, not influence. The line is not made of anything. It is made of the rules. So what happens if we try to get there anyway? What happens if we pick a direction, point a ship, and travel? That is the question that organizes everything that follows. Because the answer is going to be wonderfully, infuriatingly, beautifully strange. We are going to chase the edge. We are going to break the speed limit to do it. We are going to arrive at every boundary the universe seems to offer, and at every single one, the boundary will have moved, or vanished, or become something we did not expect. This is not a geography problem. That is the first thing to understand. We are not asking where something is. We are asking what kind of relationship binds us to the rest of the universe, and what kind of relationships the universe permits at all. The edge of the universe, whatever that turns out to mean, is not a place, it is a condition. And the further we push, the more we are going to find that the condition is not really about the universe at large. It is about you, the observer, sitting in the middle of your own private cosmos, watching your own private horizon close in around you in a way that nobody else in the universe sees the same way. There is one more thing I want to tease before we descend into the first edge. By the time we get to the last part of this story, we are going to flip the entire question inside out. The answer is not going to be out there. The answer is going to be around you. And once you see it that way, you cannot unsee it. The universe has an edge. It just is not where you thought it was, and it is not shaped like you thought it was, and it is centered on something you would not have guessed. But before any of that, before any inversion or reframing or philosophical payoff, we have to start with the most basic version of the edge, the one your eyes can actually find, the one your telescopes can actually point at, the one that looks the most like a wall and is the most spectacular lie of the four. Because there is a sphere around us, glowing faintly in microwaves, that has been called the edge of the visible universe for over half a century. And the moment you understand what it actually is, you realize it is not an edge at all. It is a clock. Part 2. The first edge. The visible wall that isn't there. The first edge of the universe is not really an edge. It is a deadline. When astronomers talk about the observable universe, they are talking about what is technically called the particle horizon. It is the maximum distance from which light has had enough time since the beginning of the universe to reach us. Anything closer than that boundary, we can in principle see, given a powerful enough telescope. Anything farther than that boundary, we cannot, because the light from those regions simply has not arrived yet. The universe is roughly 13.8 billion years old. Light moves at a finite speed. Therefore, there is a maximum reach to our vision. Simple, except the boundary is not at 13.8 billion light-years away. It is at 46.5 billion light-years away. And the moment you understand why, you realize that this entire concept is a different beast than you thought. Light leaves a distant region of the early universe. It travels toward us for billions of years. While it is traveling, the space it is moving through is itself expanding. So by the time the light arrives at our telescopes, the place that emitted it is much farther away than it was when the photon left. The photon traveled 13.8 billion years through space, but space stretched while the photon was in transit, and the present location of the original source is now around 46.5 billion light-years away. The light is old. The source has moved on. We are looking at a postcard from a place that does not exist at that location anymore. This is the first thing the particle horizon teaches you. When you look out at the universe, you are not looking across space. You are looking back through time. The farther out you point your telescope, the deeper into the past you are looking. The Andromeda galaxy is 2.5 million light-years away, which means the light hitting your eye left there 2.5 million years ago. You are seeing Andromeda as it was when the earliest members of our genus were first picking up sticks in East Africa. The most distant galaxies the James Webb Space Telescope has photographed are over 13 billion years old. We are seeing them as they were when the universe itself was less than 1 billion years old. And at the absolute limit of vision, the edge of the particle horizon, you are not looking at a galaxy at all. You are looking at the universe itself when it was 380,000 years old. This is the cosmic microwave background, and it is the closest thing the universe has to a wall, and it is not a wall at all. It is the moment in cosmic history when the universe finally cooled down enough for the first atoms to form. Before that, for the first 380,000 years after the Big Bang, the universe was a glowing plasma, protons, electrons, and photons all smashing into each other at temperatures that would make the inside of a star look refrigerated. Photons could not travel in straight lines. They would move a tiny distance, hit a free electron, scatter, hit another, scatter again. The universe was opaque, like the inside of a thick fog, glowing white-hot. Then, as the universe expanded and cooled, the temperature dropped to about 3,000 Kelvin, which is roughly the surface temperature of a cool star. At that temperature, electrons finally slowed down enough to be captured by protons. Atoms formed. Specifically, hydrogen formed. And suddenly the universe was transparent. The fog cleared. Photons that had been bouncing around for hundreds of thousands of years could finally fly free. They have been flying ever since. When we look out at the cosmic microwave background today, we are seeing those exact photons. Some of the very same particles of light that were released at the moment of recombination, 380,000 years after the Big Bang, are arriving at our detectors right now. They have been traveling for 13.4 billion years. They left when the universe was a hot, opaque plasma transitioning to a transparent gas, and during their journey, the universe expanded so much that those photons, which started out as hot, visible, and ultraviolet light at 3,000 Kelvin, have been stretched and redshifted down to microwaves at about 2.7 Kelvin, just a few degrees above absolute zero. This is what the particle horizon actually is. It is not a wall in space. It is the edge of visible history. It is the moment in the universe's past beyond which we cannot, even in principle, see, because before that moment, light could not travel freely. We could build a telescope 1,000,000 times more powerful than anything we have today, and we would not be able to see past it. Not because there is nothing on the other side. There is plenty on the other side. The first 380,000 years of cosmic history are on the other side. We just cannot see them with light, because light could not escape the fog. Imagine standing in the middle of an enormous spherical room, and the walls of the room are glowing, and that glow is the same in every direction you look. That is what the cosmic microwave background looks like. It surrounds us. It is not in front of us. It is not above us. It is everywhere, equally, in every direction, because what we are seeing is not a place, we are seeing a time. The moment of recombination happened everywhere in the universe at once, and the light from every part of it that was the right distance away to reach us now is arriving simultaneously from all directions, forming a sphere of microwaves with us at the center. And here is where the central thread of this whole story starts to show its hand. That sphere is centered on us, not on the universe, on us. An astronomer in a galaxy 10 billion light-years away would also see a sphere of cosmic microwave background, but their sphere would be centered on them, not on us. There is no privileged center. The visible universe is not some object floating in space with a single edge. The visible universe is a relationship between an observer and the speed of light and the age of the cosmos. Every observer has their own observable universe, their own particle horizon, their own sphere of microwave background. The cosmic microwave background is also not perfectly smooth. When you look at it carefully, with instruments like the Planck satellite or its predecessors WMAP and COBE, you find tiny ripples in temperature, about 1 part in 100,000. Some patches of sky are slightly warmer than 2.725 Kelvin. Some are slightly cooler. These ripples, these anisotropies, are the seeds of everything. Every galaxy, every star, every planet, every person, every atom in your body, all of it grew out of those tiny temperature differences in the infant universe. The places that were slightly denser collapsed under gravity to form the first stars and galaxies. The places that were slightly less dense became the cosmic voids. You are, in a very real sense, looking at the blueprint of yourself when you look at the cosmic microwave background. The other thing the cosmic microwave background does is tell us how we are moving. Earth is not stationary relative to it. We are moving through space, relative to the average rest frame of the cosmic microwave background at about 370 kilometers per second, in the direction of the constellation Leo. We know this because the half of the sky we are moving toward looks slightly hotter, and the half we are moving away from looks slightly cooler due to the Doppler effect. So even the cosmic microwave background, this seemingly absolute reference, gives different readings to different observers. There is no place to stand in the universe that gives you the universe's true frame. There are only your frame, and my frame, and every other observer's frame, each with their own slightly different sphere of ancient light. Now, here is the question that should be forming in your mind. If the particle horizon is just a time horizon, just a boundary defined by how long light has been traveling and how fast it moves, and how old the universe is, then is it really an edge in any meaningful sense? Or is it just a coincidence of when we happen to be looking? Because here is the thing about time horizons. They expand. Every second that passes, the universe gets a little older. Light has had a little more time to reach us, and the particle horizon grows. New galaxies, galaxies whose light had not yet had time to get here, slowly become visible. The observable universe is bigger today than it was yesterday. It will be bigger tomorrow than it is today. The wall, if you want to call it that, is retreating from us at the speed at which time is progressing. So this first edge, this beautiful glowing sphere of ancient microwaves, is not actually trapping us. It is just the current setting of a cosmic clock. Wait long enough and you can see past it. Wait long enough and the sphere widens. The visible universe, in this sense, is not a confinement. It is a window that keeps opening. Which makes you wonder about the other edge, the one we mentioned at the beginning, the one at 16.5 billion light-years, the one that is closer than the particle horizon, the one that is shrinking, not growing, the one that, instead of letting us see more over time, lets us reach less, because that one is a different animal entirely. That one is not a clock, that one is a cage, and it is closing. Part 3. The journey that can never finish. So you decide to chase it. You build the most extraordinary spacecraft humanity has ever conceived, accelerate to within a hair's breadth of the speed of light, point yourself at the most distant galaxy your telescopes can resolve, and you go. The light from that galaxy is arriving in your eyes. The galaxy itself sits, by current measurements, about 30 billion light-years away, in proper distance. You think to yourself, all right, 30 billion years at light speed, give or take. A long trip, but finite, possible. You are wrong. You will never get there. Not because your ship breaks down, not because you run out of fuel, not because of any contingency you could fix with better engineering. You will never get there because the space between you and that galaxy is expanding faster than you can cross it. Every meter you traverse, the universe adds new meters ahead of you. The road is being laid down faster than you can drive it. You can drive forever, at the maximum speed the universe permits, and the destination will keep retreating, and you will never arrive. This is what the expansion of space actually means. It is one of the most counterintuitive facts in modern physics, and it sits right at the center of why the edge of the universe is not what you think it is. So let us slow down and pull this apart, because this is the engine that drives everything else. The expansion of the universe is not motion. That is the first thing to get straight. When two distant galaxies are flying apart from each other, at what looks like, from our perspective, faster than the speed of light, neither of those galaxies is actually moving through space at superluminal velocity. Locally, in their own neighborhoods, they are barely moving at all. They might be drifting through their local cluster at a few hundred kilometers per second, well below the speed of light. What is happening is that the space between them is stretching. New space is being created, continuously, everywhere, all the time. The galaxies are not running, the track is growing. This does not violate Einstein's special relativity. Special relativity says nothing local can move through space faster than light. It says nothing about how fast space itself can expand. There is no speed limit on the metric of space-time. Space can do whatever it wants. And what it is doing throughout the cosmos every second is adding distance. The current rate of expansion is described by what cosmologists call the Hubble constant. The most recent measurements put it at around 67 to 73 kilometers per second per megaparsec, depending on which method you use. There is actually a pretty famous tension in cosmology right now over which of those numbers is correct, but for our purposes, what matters is what it means. For every megaparsec of distance between 2 points in space, those points are getting farther apart by about 70 kilometers every second. A megaparsec is about 3.26 million light-years. So, a galaxy 3.26 million light-years away from us is receding from us at 70 kilometers per second, just from the expansion of space itself. That sounds modest. But the relationship is linear. Double the distance, double the recession speed. A galaxy 6.5 million light-years away is receding at 140 kilometers per second. A galaxy a billion light-years away is receding at 20,000 kilometers per second. And once you get out to about 14.4 billion light-years of distance, the recession velocity, due to expansion alone, equals the speed of light. This distance, where the rate of expansion-driven recession matches the speed of light, has a name. It is called the Hubble sphere, or sometimes the Hubble horizon. It sits at about 14.4 billion light-years from us. And here is where things get strange, and where the central thread of our story tightens. Galaxies beyond the Hubble sphere are receding from us due to the expansion of space, faster than the speed of light. And yet, we can still see them. Their light is still reaching us. The particle horizon, remember, sits at 46 billion light-years, far beyond the Hubble sphere. How is that possible? How can light from a galaxy that is moving away from us faster than light still reach us? The answer is that the photons are not racing the galaxy. They are crawling through space, 1 meter at a time, while space itself is stretching. The photon makes progress in its local frame, but the global geometry it is moving through is changing. In the early universe, when space was expanding more slowly relative to its size, photons emitted from very distant regions could make headway. They got caught in regions of space that were not stretching as fast as they were moving, and they got dragged along with the expansion until they reached us. The light from the cosmic microwave background, the light from the most distant galaxies, all of it is light that has been struggling against expansion for billions of years and just barely making it. But there is a limit to that struggle. Once expansion is fast enough, and once the destination is far enough, photons leaving a source today will never reach us. Not because they slow down, they do not. Photons always move at the speed of light locally, but the space they are trying to cross grows faster than they can traverse it. They make progress, but they fall behind. They asymptotically approach, but never arrive. So the question becomes, where does that boundary sit today? Where is the line, right now, between sources whose light can still reach us and sources whose light, emitted today, will never make it? That line is called the cosmic event horizon, and it sits at about 16.5 billion light-years from us. Anything beyond that distance, anything emitting light or radio waves or any signal at all today, will never be detectable by us, ever. Even with infinite time, even with infinite patience, the space between us is stretching faster than the signal can cross it, and that gap is widening, not narrowing. Now here is what really hits. The particle horizon, the edge of what we can see, sits at 46 billion light-years. The event horizon, the edge of what we can ever reach or be reached by, sits at 16.5 billion light-years. There is a 30 billion light-year gap between those two boundaries. That entire region, an unimaginably vast volume of the universe, contains galaxies whose light is currently arriving at our telescopes, but whose present moment we will never know. We are seeing them as they were billions of years ago, while their actual location, their actual present state, has long since drifted into the unreachable. Their photons are fossils from a time when they were closer. The galaxies themselves, today, are gone from our future light cone. Think about that for a moment. Take it slow. There are galaxies in your night sky right now that are causally disconnected from you. Whatever is happening in them at this moment, they could send out a flash so bright it would turn night into day, and we would never see it. Whatever civilizations might be there, sending out radio signals, broadcasting their existence, hoping someone is listening, none of that will ever cross the gap. They are visible, but unreachable. They are there, but not there. They are ghosts of a younger universe, and the universe has aged past them. This is the moment in the story where the central thread becomes impossible to ignore. The edge of the universe is not a place. Visibility and interaction are not the same thing. The fact that you can see something does not mean you can reach it. The fact that you have evidence of something does not mean you can ever influence it. The universe permits witnesses to events they cannot participate in. The universe, in other words, is a one-way mirror in some directions. And the photon you imagined, the one you sent racing toward the edge, will never catch it. Not because the edge is moving fast, not because the photon is slow, But because the geometry of the universe is arranged such that the relationship between the photon and the destination is one of asymptotic approach without arrival, the photon will get closer and closer. It will keep going forever. And the destination will keep receding, the universe will keep adding distance, and no finite amount of time will ever be enough. The edge, in this picture, is not a place. It is a condition. It is the condition of being separated by more space than light can cross before more space appears. It is not somewhere you can stand. It is not somewhere you can point to. It is a relationship, a function of where you are and when you are looking and how fast the universe is expanding. Which raises the next question, the one that should be burning a hole in your mind right now. If this edge can be defined just by the rate of expansion, and if the expansion is accelerating, then the edge is changing. It is shrinking. It is getting closer. The cosmic event horizon, as we defined it, is contracting in proper distance over time, because as expansion accelerates, the radius within which we can causally reach gets smaller. Right now, we can reach things up to 16.5 billion light-years away. In the distant future, that number will be smaller, much smaller. And eventually, almost everything we can currently see will be beyond our event horizon, on the other side of a line that is closing in around us. That is not a metaphor. That is not poetry. That is the actual prediction of standard cosmology under accelerating dark energy. The universe is, in a real and measurable sense, becoming smaller from our perspective. The pocket we inhabit, the region with which we can ever causally interact, is shrinking. And if it is shrinking, then it is doing something to us. It is taking things. Galaxies are crossing that boundary right now, tonight, while you are listening to this. They are slipping out of our future, even as their light continues to arrive in our present. It is a slow-motion vanishing act, happening on cosmic timescales, but happening all the same. The universe is closing around us, one galaxy at a time, and nobody designed it that way. Nobody is doing it on purpose. It is just what the laws of physics produce when you let them run. Which means the next question is the one that gives this story its emotional weight. What does it actually feel like? What does it actually mean to live in a universe that is removing itself from your reach? What is on the other side of that horizon after the crossing? And is there any way at all, to chase it down before it disappears? Part 4. The second edge, the one you can't escape. The cosmic event horizon is the cruelest boundary in physics, because it is the one that stops you not by blocking your path, but by erasing your future. Let me put it in terms that are blunt and exact. The cosmic event horizon is the radius around you right now, beyond which any signal you send today, no matter how powerful, no matter how cleverly engineered, will never arrive, not in any future. Not under any circumstances. The space between you and anything beyond that radius is expanding too fast for your signal to bridge it. You can shout. The shout will travel forever, but it will never reach the listener, and it will never be heard. In our universe, with the dark energy density and the matter content we currently observe, that radius sits at approximately 16.5 billion light-years. The exact number depends slightly on which set of cosmological parameters you use, but the Planck 2018 results, combined with subsequent refinements, put it firmly in that range, 16.5 billion light-years. That is your maximum sphere of influence. That is the volume of the universe you, sitting where you are right now, can causally affect, even if you had infinite time and infinite resources. Now compare that to the particle horizon. The particle horizon, the edge of the visible universe, is at 46.5 billion light-years. So the universe you can see is roughly 30 billion light-years bigger in radius than the universe you can ever influence. The volume of the visible universe is about 18 times larger than the volume of the reachable universe. We are observers of a domain that is enormously larger than the domain we are participants in. We watch a universe whose majority is, in the deepest sense of the word, beyond us. This distinction between the particle horizon and the event horizon is the key to the whole story. The particle horizon is about the past. It tells you how far back in time you can see, given that light moves at a finite speed. The event horizon is about the future. It tells you how far forward in influence you can reach, given that space is expanding at an accelerating rate. The reason they are different is that the universe is not just expanding, it is accelerating. And it is accelerating because of dark energy, which we know exists because of careful measurements made starting in 1998. When two independent teams looking at distant supernovae discovered that the expansion of the universe is not slowing down, as everyone had expected. It is speeding up. Something is pushing space apart, and the more space there is, the more pushing happens, in a kind of cosmic feedback loop. The current best estimate is that dark energy makes up about 68.5% of the total energy content of the universe. Matter, both ordinary and dark, makes up the rest. And dark energy, whatever it actually is, has been driving accelerated expansion for the last several billion years. This acceleration is the engine that creates the event horizon. In a universe that was decelerating, like the one cosmologists thought we lived in until the late 1990s, there would be no event horizon. Light could always eventually catch up to its destination, given enough time. But in a universe that is accelerating, where the rate of expansion is itself growing, there comes a point where the gap is widening too fast. And once a region of space is past that point, no signal can ever bridge the divide. What makes this so brutal is that it has nothing to do with technology. I keep coming back to this because it is the part the brain refuses to accept. We are a species that has gotten very good at solving problems. We invented the wheel, the steam engine, the airplane, the rocket, the computer, the internet. Every time we have hit a wall, we have eventually figured out how to climb over it, dig under it, or tunnel through it. So when somebody says there is a place you cannot reach, the natural human response is to say, give us time, we will figure something out. But this is not a problem that admits a solution. This is geometry. This is the structure of space-time itself. The gap between you and a galaxy beyond your event horizon is not a gap of distance. It is a gap of causality. It is a region where the relationship between events does not permit any line of communication. There is no faster ship, no cleverer engineering, no breakthrough technology that can change this. You would have to change the rules of the universe itself. And here is the part that is genuinely heart-stopping when you sit with it. This applies to galaxies you can see. Right now. Tonight. There are galaxies in your observable universe whose light is currently reaching your telescopes, whose images you could pull up on a screen if you had access to the right data, whose existence is a matter of empirical record that are already, today, beyond your event horizon. You can see them. You cannot affect them. They sit on the other side of the line. Their photons are still arriving from when they were closer, but their present locations, their present states, are unreachable. This is what happens when the rate of expansion has been accelerating for long enough. Galaxies whose light started traveling toward us when they were within our reachable sphere are still delivering that light, even though they themselves have crossed the boundary in the meantime. The photons made it out before the gate closed. The galaxies did not. The cosmic event horizon, like all the other boundaries we have been discussing, is centered on the observer. It is not a feature of the universe at large. It is a feature of your relationship with the universe. Somebody in another galaxy, 10 billion light years from here, has their own cosmic event horizon, also at about 16.5 billion light years from them. Some of the galaxies inside their horizon are inside ours. Some are not. Some are inside ours, but not inside theirs. The horizons overlap and intersect and slide past each other in a vast cosmic web of causal pockets. There is no single event horizon for the whole universe. There is only your event horizon, and mine, and every other observer's. And this horizon, unlike the particle horizon, is not expanding, it is contracting in proper distance. As dark energy continues to accelerate the expansion of space, the radius within which you can causally reach is getting smaller, year by year, eon by eon. Not by much, on human timescales. The change is glacial in the most literal sense, but it is happening, and over cosmic timescales, it is decisive. The reachable universe is shrinking around you. This is the central reality the rest of this story keeps circling back to. The edge of the universe, the meaningful edge, is not some distant wall. It is a closing horizon centered on you, defined by physics you did not choose, drawing in at a rate you cannot affect. The universe is not expanding into something. It is expanding away from itself, in every direction, for every observer, with everyone watching their own personal cosmos quietly become more isolated. Causal disconnection is the term for what happens when something crosses the event horizon. After the crossing, two regions of space-time can no longer exchange information. They can no longer affect each other. Whatever happens on one side cannot, in principle, be known on the other side. They might as well be in separate universes. Functionally, they are in separate universes. The causal pocket on each side is sealed off from the other forever. And right now, this causal disconnection is happening in real time. Galaxies are crossing your event horizon while you are listening to this. Some have already crossed. Some are crossing now. Some will cross tomorrow. The boundary is not static. It is dynamic, and it is moving inward, and the universe is, in the strictest sense, getting smaller from your point of view. Which leads, naturally, to the question that has probably been forming in your head for the last several minutes. If this is happening, if galaxies are slipping past the edge in real time, what does it actually look like? Can we observe it? Can we point a telescope at the boundary and watch the universe disappear? The answer is yes, in a sense. And the way that yes works is one of the strangest things in observational cosmology, because the galaxies do not vanish, not visually, not for a very, very long time. They do something far more haunting than disappear. They linger. They hang there in the sky like photographs of a dead person perfectly visible, while the actual person has long since passed beyond any door we could open. Part 5. Watching the universe disappear in real time. When a galaxy crosses your cosmic event horizon, it does not blink out. It does not fade in some dramatic farewell. It just keeps shining, at first, almost as if nothing happened. And that is the strangest thing about this slow vanishing. The crossing is silent. The crossing is invisible. The galaxy goes on broadcasting, and we go on receiving. And the connection feels alive, even though it is, by every measure that matters, already severed. Here is how it actually works. A galaxy at the cosmic event horizon, 16.5 billion light-years away, is at the boundary where signals it sends today will just barely fail to reach us. But signals it sent yesterday, or 1,000,000 years ago, or 1,000,000,000 years ago, when it was closer to us in proper distance, are still in transit. Those photons left when the geometry was friendlier. They are still on their way, and they will keep arriving for an enormous amount of time, possibly billions of years, slowly redshifting, slowly fading, but always there, always present in our sky. This is the eerie thing about the cosmic event horizon. It is not a sharp visible boundary. From our point of view, watching the sky, we cannot tell which galaxies are inside our horizon and which are outside. The crossing is invisible in real time. A galaxy can have just slipped beyond the edge yesterday, and to us, tonight, it looks exactly the same as it did the night before. The light keeps coming. Only the future has changed. Only the relationship has shifted. Imagine watching a live video feed from a friend in another country. The image is beautiful, the connection is clear, you feel like you are in the same room. Now imagine that, halfway through the call, The network cable connecting your two countries is severed, but the buffer of footage already in transit keeps playing. You see your friends smiling, talking, gesturing for hours, maybe days, while the signal already in flight slowly empties out. They look fine, they look present, but you cannot reply. You cannot ask them anything. Anything you say from this point on will never reach them. You are watching a recording disguised as a live feed. The friend is gone, or rather, you are gone to them, and they are gone to you. But the appearance of presence persists because the photons that left before the disconnection are still finding their way to your eyes. That is what watching the universe disappear looks like. It is not dramatic. It is not loud. It is a quiet attenuation of relationships, a one-way conversation that lasts for cosmic ages, while the actual link has long since broken. What does change, slowly, is the light itself. As galaxies cross the event horizon and continue receding into the accelerating expansion, their light gets stretched. The redshift, the increase in wavelength of light from receding sources, grows over time. A galaxy that emitted a photon in the visible spectrum 1 billion years ago might now be sending us photons that have been redshifted into the infrared. A galaxy whose light was once detectable will, over enough time, have its emissions redshifted out of any wavelength we can detect. The signal does not stop. It just shifts further and further toward the long wavelength end of the spectrum, until eventually it is so stretched, so attenuated, that no instrument we can build can pick it up. This process is slow, but it is relentless. Over hundreds of billions of years, the galaxies beyond our event horizon will redshift into oblivion, not because they ceased to exist, but because the expansion of space has stretched their light beyond any practical detectability. The sky will grow darker, slowly, galaxy by galaxy, as the universe quietly removes its evidence of itself. There is a famous calculation made by the physicists Lawrence Krauss and Robert Scherer in 2007 that lays out what this means for the long-term future of cosmology. They worked out what an observer in a galaxy like ours would see, far enough into the future that the accelerating expansion has done its full work. Their conclusion is one of the most haunting in modern physics. They estimated that in roughly 100 billion years, the only galaxies still visible from our location will be the members of our own gravitationally bound group, the local group, which includes the Milky Way, Andromeda, the Triangulum Galaxy, and a few dozen smaller satellite galaxies. Everything else will have receded so far, redshifted so deeply, that it will be invisible. By that point, the Milky Way and Andromeda will likely have merged, forming a single elliptical galaxy, sometimes called Milkomeda. Our descendants, if any of them still exist in any form, will look out at the night sky and see a single island of stars, surrounded by an apparently empty void. They will not see the rest of the universe. They will not see the cosmic microwave background, which by then will have redshifted to wavelengths beyond any reasonable detector. They will have no astronomical evidence of the Big Bang. They will see only their local cluster of stars, embedded in what looks like an infinite, eternal, static darkness. Think about what that means. An entire civilization, an entire scientific tradition would conclude, based on what they could observe, that the universe consists of a single galaxy in a static void. They would have no way of knowing that there are trillions of other galaxies out there. They would have no way of knowing that the universe is expanding. They would have no way of knowing that there was a Big Bang. The empirical record of those facts will have been redshifted into invisibility. The truth will be unknowable to them, even with arbitrarily good technology, because the data simply will not exist within their causal pocket anymore. That is what the central thread of this story keeps insisting on. The universe is not an objective thing with a single description. The universe, observationally, is what your causal pocket allows you to see, and causal pockets shrink. Information disappears. Knowledge becomes inaccessible. Future cosmologists, by the very physics that produces accelerating expansion, will have less data to work with than we do. They will know less than we know, not because they are less clever, but because the universe will have hidden more from them. This is sometimes called the island universe scenario, and it is the projected fate of every observer in an accelerating universe. Each observer, eventually, becomes isolated within their own gravitationally bound region, surrounded by causally disconnected darkness. The cosmic event horizon will, over enough time, contract until almost nothing is inside it except the local matter that is gravitationally bound. The universe will appear to consist of one galaxy and a void, and that appearance will be all the empirical truth available. The thermodynamic implication of this is also worth pausing on. As the universe expands and matter is diluted and information becomes inaccessible, the universe is, in a real sense, approaching a kind of cosmic isolation. Entropy continues to increase. Useful energy gradients continue to flatten. The structures we know, galaxies, stars, planets, eventually exhaust their fuel. Stars burn out over trillions of years. Galaxies fade. The universe, on long enough timescales, becomes a sparse, cold, dark place, and each observer is more and more alone within their shrinking causal pocket. There is something genuinely strange about being alive in this particular era of the universe. We are early. We exist in a moment when the cosmic microwave background is still detectable, when distant galaxies are still visible, when the structure of the universe is still legible from where we sit. We are in the brief window of cosmic history during which the question of where the edge of the universe is can even be meaningfully investigated because the data is still here. In 100 billion years, that window closes. The questions become unanswerable. The universe becomes opaque to itself. So the central reality is this: the edge of the universe is closing around us, and we can watch it close. Galaxies are crossing the boundary tonight. Their light will keep arriving for billions of years, but the connection is severed. The universe is not just remote, it is becoming, second by second, more remote, and each observer, in their own causal pocket, watches the universe slowly switch off beyond their reach. This raises a question that physicists have been chewing on for decades. If this is the situation, if the universe is closing around us due to the geometry of space-time, is there any way around it? Is there any loophole in physics, any clever trick, any speculative technology that could let us beat the expansion and reach those vanishing galaxies before they slip away forever? You probably know what comes next. The dream of warp drive is older than most of the science we have used so far, and it is, surprisingly, not as ruled out as it might sound. But even if it works, even in the most optimistic scenarios, it does not save us from the central problem. We will see why. Part 6. Breaking Physics, the Warp Escape Attempt. The idea of moving faster than light has haunted physics for 100 years. It haunts us because relativity is so airtight on the local question. Locally, in any small region, nothing can outrun a photon. Particles with mass cannot reach light speed, let alone exceed it. The universe is structured to forbid it, and yet the expansion of space itself does not obey that local rule. Space can stretch faster than light. So the question physicists keep returning to is whether we can use space's loophole to do something massive objects cannot do on their own. In 1994, the Mexican physicist Miguel Alcubierre published a paper that gave this dream a mathematical skeleton. He proposed a metric, a specific configuration of space-time in which a region of space could be contracted in front of a spacecraft and expanded behind it, while the spacecraft itself sat in a flat bubble of normal space in the middle. The ship would not be moving through space. The space around it would be moving, carrying it along like a surfer riding a wave. Locally, inside the bubble, everything would seem normal. No relativistic time dilation, no infinite mass, The ship would just sit there, while the universe rearranged itself to deliver it to its destination. The original Alcubierre solution was thrilling and devastating in equal measure. It was thrilling because it was a real, general relativistic solution, not science fiction. The math worked. It was devastating because it required exotic matter with negative energy density, something physics has never observed and may not even permit in any practical quantity. The amount of negative energy required in the original formulation was on the order of the mass of Jupiter, or in some calculations, the mass of the entire observable universe. Either way, not buildable. For decades, the Alcubierre drive sat in the territory of beautiful equations with no physical realization, but more recently, things have started to shift. In 2021, the physicists Alexei Bobrik and Gianni Martier published a paper showing that the original Alcubierre framework was a special case of a much broader family of warp solutions, and that some of those solutions might be achievable with positive energy and ordinary matter. They redefined what counts as a warp drive in a more general way, and they showed that subluminal warp drives, ships moving slower than light but using space-time distortion, are physically permissible without exotic matter. The paper sparked a wave of new investigation. Then Eric Lentz, in 2021, proposed a soliton-based solution that used positive energy densities to construct stable warp shells. The idea was that you could engineer a self-reinforcing wave of curved spacetime, a soliton, that would move through the universe carrying its passengers along, without requiring any exotic matter. The energy requirements are still astronomical, but they are no longer fundamentally impossible. They are just absurdly large. In 2024, a research group led by Jared Fuchs published further refinements demonstrating that stable, subluminal warp shells are buildable in principle from ordinary matter, given enough of it. The picture that has emerged is that warp drives, in some form, do not violate general relativity. They sit within the rules. The remaining problems are engineering problems, and the engineering problems are extreme, but they are not theoretical impossibilities. What this all means is that the speed of light, locally, is still inviolable. A warp drive does not let you outrun a photon in your local frame, but it lets you fold space in effect, so that the global distance you traverse is much shorter than the path through ordinary space would suggest. You are not moving through the universe faster than light. You are rearranging the universe so the trip is shorter. And in principle, this could let you reach galaxies that, by ordinary travel, would be receding faster than you could chase them. So let us grant the dream. Let us assume, for the sake of argument, that humanity, or its successors, build a working warp drive. Let us assume that energy is no obstacle, that engineering is no obstacle, that all the practical problems get solved, and we have ships that can warp through space at effective velocities far greater than the speed of light. We point our ship at the cosmic event horizon. We accelerate. We chase the edge. Here is the central thread reasserting itself. Even with a warp drive, even if we can move arbitrarily fast through warped space, the cosmic event horizon does not become a wall we can break. It becomes a horizon we can extend. We can reach galaxies further out than we could have reached without warp. We can extend our causal pocket. We can see, perhaps, vastly more of the universe than the unmodified physics allowed. But every place we go, we arrive at a new local frame, and from that new local frame, there is a new event horizon. The horizon is not a thing we can leave behind. The horizon is a relationship that travels with us. This is the deeper lesson that the warp drive thought experiment teaches. The cosmic event horizon is not a barrier of speed. It is a barrier of geometry, defined by the relationship between observers and the expansion of space they inhabit. You can change your speed, you can change your position, you can change your frame, but you cannot escape having a horizon, because the horizon is a feature of the observer, not the universe. Wherever you go, your horizon goes with you. It rides on your shoulder. It defines your causal pocket from your own location, and it always sits at roughly 16.5 billion light-years away in our particular cosmological era. The warp drive does not break the central thread, it confirms it. Even breaking the local speed limit, even folding space at will, even crossing what looked like an unreachable distance, you still find yourself in a universe with an event horizon. The horizon has moved with you. It is centered on you. It always will be. The edge of the universe, in this sense, is not something you can outrun by going faster. It is something that follows you around because it is built out of your relationship with everything else. But of course, we are not going to stop here. We are going to keep going. We are going to ride this hypothetical warp ship past every boundary the universe seems to offer, just to see what happens. Because the next question is what we find when we arrive at what looks like the wall. What does the edge of the visible universe look like when you actually get there? You might be expecting darkness, or fire, or a final frontier of some kind. What you get, instead, is something deeply ordinary and deeply strange and deeply revealing about why the question of edges does not work the way you thought. Part 7. Arrival, where the edge was supposed to be. You arrive at the edge of the visible universe, 46.5 billion light-years from where you started. You step out of your warp ship, you look around, and you see exactly what you have always seen. Galaxies, stars, the familiar texture of the cosmos. There is no wall, there is no boundary. There is no surface where the universe ends. There is just more universe, going on in every direction, looking remarkably like the universe you left behind. This is the moment where the entire question of where the edge of the universe is finally collapses. Because there is no edge here. There never was. The edge you flew toward was not a feature of the universe at large. It was a feature of your old observation point. The particle horizon, at 46.5 billion light-years, was the edge of what you could see from Earth. It was never the edge of what is. And now that you are standing somewhere else, your particle horizon has moved with you. It is still 46.5 billion light-years, but now it is 46.5 billion light-years from your new location. The edge has not been reached. It has been reset. This is what cosmologists mean when they say horizons are observer-dependent. The boundaries we have been talking about, the visible universe, the reachable universe, the cosmic microwave background sphere, all of these are defined relative to where the observer is sitting. Move the observer, and the boundaries move with them. The universe does not have a single edge that everyone agrees on. The universe has an edge for you, and another edge for me, and another edge for every other observer in the cosmos. And each of those edges is centered on its respective observer. So when you arrive at what was, from Earth, the farthest point you could see, you find yourself surrounded by a perfectly ordinary local cosmos. Galaxies are sprinkled around you in roughly the same density they were sprinkled around the Milky Way. Stars shine. The cosmic microwave background still glows in every direction. A sphere of 2.7 Kelvin radiation, except now the sphere is centered on you, not on Earth. And here is the part that breaks the brain. From this new position, you point your telescopes back toward where Earth was, where the Milky Way still is, and you see, at the very edge of your visibility, a faint glow of the early universe. The same glow Earth-bound astronomers see in the opposite direction, because from your new location, the Milky Way region of space is now in the deep distance, in the deep past, on the boundary of your visible universe. The Milky Way looks, to you now, like one of those impossibly distant, high redshift galaxies that astronomers on Earth study with the James Webb Space Telescope. It is a smudge of light from a young universe, frozen in the past from your perspective. This is the inversion. The point you came from is now at the edge of what you can see. The home you left is, from this vantage, an early universe artifact. And that is not because the home itself has changed. It has not. The The Milky Way is still there, doing its thing. It is your relationship to it that has changed. From this new location, the Milky Way is far away, and its light, traveling at the finite speed of light, is reaching you from billions of years in your past. You are seeing it as it was, not as it is. And from its perspective, you are now in the same situation. You have become the distant smudge. This is what relational cosmology actually means. The universe does not have a privileged center. It does not have a privileged edge. Every position in the universe is, from its own perspective, the center of its own observable cosmos. Everywhere, in this sense, is the middle. There is no place you can stand that is special. There is no place you can stand that is the boundary. The boundary moves with you because the boundary is part of you, in a sense. It is the geometric expression of your finite presence in an infinite or quasi-infinite space. The phrase that captures this, and that astronomers have been using for decades, is that the universe looks the same everywhere on large scales. The cosmological principle. Pick any point, any random galaxy, anywhere in the cosmos, and the view from there will be statistically indistinguishable from the view from here. Same density of galaxies, same distribution of large-scale structure, same glow of cosmic microwave background, same accelerating expansion. The universe is, in this sense, a place where everywhere is interchangeable, and where no point can claim to be special, and where the boundaries of observation depend entirely on who is asking. So, if there is no edge in this sense, no wall you can fly to, no frontier you can plant a flag on, then what is the universe? What is its shape? Is it infinite? Is it finite but unbounded? Does it loop back on itself somehow? These questions become unavoidable once you realize that the visible boundary is just a function of where you are, not of what is. The actual structure of space, the actual geometry of the universe, has to be understood at a different level entirely. And this is where things get strange in a different way. Because the universe, geometrically, has several possible shapes, and our measurements have not fully ruled any of them out, we have constraints, we have data, but we do not have certainty. The universe could be flat and infinite, stretching out forever in every direction with no boundary anywhere. It could be curved and finite, like the surface of a four-dimensional sphere, where you could in principle travel in a straight line and eventually return to your starting point. It could even be wrapped around itself in a more exotic topology, like a cosmic donut, where space loops in unexpected directions. None of these shapes give you an edge. None of them. Even the finite ones do not have a boundary you can hit. They are finite the way the surface of a balloon is finite. You can travel forever on the surface of a balloon without ever falling off, because the balloon is curved back on itself. There is no edge. There is just a finite amount of space, looped in a way that lets you keep going indefinitely. So the next question, the question we have to take seriously, is what shape the universe actually has. Because that shape determines whether the apparent infinity we see when we travel is real infinity or a clever illusion of finite space wrapped on itself. And the answer to this question, from the best data we have, is genuinely peculiar, with hints in the data that the universe might be subtly closed, even though most of the evidence points to flatness. And the resolution of that tension is an open question in current cosmology. Either way, the edge you were looking for is not in the geometry. The geometry refuses to give you a wall. It only gives you, at most, a loop. Part 8. The shape of a universe without edges. The shape of the universe is encoded in a single number called the curvature parameter, written as omega k, and the most precise measurement of it we have from the Planck satellite, combined with other large-scale surveys, places it at approximately 0.000 with an uncertainty of about plus or minus 0.005. That is, about as flat as anything in nature can be measured to be. The universe, on the largest scales we can probe, looks geometrically flat to within the limits of our most sensitive instruments. What does flat actually mean here? It means that the geometry of the universe obeys the rules of regular Euclidean geometry on large scales. Parallel lines stay parallel. The angles of a triangle sum to 180 degrees. The circumference of a circle is exactly 2 pi times its radius. None of these would be true in a curved universe. In a positively curved universe, like the surface of a sphere, parallel lines eventually converge. Triangles have angles that add up to more than 180 degrees, and circles have circumferences less than 2 pi times their radius. In a negatively curved universe, like the surface of a saddle, parallel lines diverge, triangles have angles summing to less than 180 degrees, and circles are bigger than they would be in flat space. We see none of these effects on cosmic scales. The universe behaves, geometrically, like a flat piece of paper, just one that happens to be three-dimensional and unimaginably large. If the universe is truly flat, then it is, almost certainly, infinite. A flat universe has no natural scale at which it has to end. It just extends indefinitely in every direction with the same statistical properties everywhere. There is no edge anywhere. You can travel in any direction for any amount of time, and you will never hit a wall, never run out of space, never find a boundary. There is just always more universe, and always the same kind of universe, all the way out. This is not a satisfying answer to the question of where the edge is, but it is, in some ways, the cleanest possible answer. The edge does not exist. The universe goes on forever. The horizons we have been discussing, the particle horizon and the event horizon, are local phenomena, defined by your observation point and the finite age of the universe, not by any global boundary in space. But here is where it gets interesting. The Planck satellite did not just measure the average curvature of the universe, it also measured tiny anomalies in the cosmic microwave background, and some of those anomalies hinted at something unexpected. In 2020, a paper by Eleonora Di Valentino, Alessandro Melchiori, and Joseph Silk pointed out that the Planck data, taken on its own, prefers a slightly closed universe. The signal was not large. It was at about the 3 sigma level of statistical significance, which is interesting but not conclusive, but it was there. The data was tilting ever so slightly towards saying that the universe is positively curved, like the surface of a 4-dimensional sphere, finite but unbounded, big enough to look flat to us, but actually closed on the largest scales. This caused something of a stir in the cosmology community, because if the universe is closed, then it is not infinite. It is a finite object, with a finite volume that we just happen to be sitting inside. There is still no edge, in the sense that you cannot reach a wall, but there is a finite total amount of space, and in principle, you could travel far enough in a straight line to come back to where you started. The complication is that when you combine the Planck data with other independent measurements, like baryon acoustic oscillations and supernova surveys, the closed universe hint disappears. The combined datasets prefer flatness. The signal from Planck alone seems to be either a statistical fluctuation or a sign of some systematic effect we have not fully accounted for, or a hint of new physics. The mainstream view today is that the universe is, to the best of our measurements, flat. But the door has not been completely closed on the possibility that it is mildly curved and finite and looped on itself in some way we have not yet detected. If the universe is closed, the minimum size of the loop is enormous. Calculations based on the lack of repeated patterns in the cosmic microwave background suggest that if the universe loops back on itself, it does so on a scale at least 800 billion light-years across. That is more than 17 times the radius of our observable universe. We are sitting inside a region that, even if it is finite, is so vast compared to what we can see that the finiteness has no observable consequences for us. We cannot detect the loop. We cannot see the seam. Our observable universe fits inside the loop with enormous room to spare. There is another exotic possibility that cosmologists have explored, called toroidal topology. The idea is that the universe might be flat in its local geometry, but wrapped around itself in a more complicated way, like the surface of a donut. In a toroidal universe, you could travel in a straight line and eventually return to your starting point, even though the local geometry is flat. There would be no curvature, but there would be a topology that wraps. Some studies have looked for signs of this kind of wrapping in the cosmic microwave background by searching for matched circles, which would be regions of sky that look identical to other regions because the same volume of space is being seen from two different angles due to the wrapping. So far, no convincing matched circles have been found. The wrapping, if it exists, is on a scale larger than our observable universe. The central thread reasserts itself here. Even the shape of the universe, even the underlying topology of space, does not give you an edge. Flat universe, infinite, no edge. Closed universe, finite but unbounded, no edge. Toroidal universe, wrapped on itself, no edge. None of these geometries produce a wall that you could fly to and bump into. The universe, at the level of geometry, simply does not include the concept of a boundary. The edge is not a feature of the shape. The edge, whatever it is something else entirely. And the something else, as we keep finding, is the horizon. Always the horizon. Always the relationship between an observer and the rest of the cosmos, never an absolute fact about the cosmos itself. This is the moment to pull the central thread tight again. The universe, as a geometric object, is not bounded. It does not have a wall. It has at most a loop, and even the loop, if it exists, is so enormous that we cannot detect it. The boundaries we keep encountering are all observer-centric. They are all about you, about where you are, about what you can reach and see. The universe at large does not have an edge. You have an edge, and so do I, and so does every other observer, and our edges are all different because our positions are different. So if the geometry refuses to give us a wall, and if every horizon we hit turns out to be observer-dependent, and if every edge dissolves on closer examination, then maybe the question we should be asking is even weirder. Maybe the question is, in a universe that might be infinite, what does that infinity actually contain? Because if space goes on forever, and if the laws of physics are roughly the same everywhere, then very strange things start happening. Things the brain refuses to fully accept. Things that, if they are true, change what it means to be you. Part 9. Infinity breaks identity. If the universe is truly infinite, then somewhere out there is another you. I do not say this for dramatic effect. I say it because it is what the math actually predicts, given a small set of assumptions that are taken seriously by serious physicists. The argument was made famous by the cosmologist Max Tegmark in a series of papers and in his book Our Mathematical Universe. But the underlying logic does not depend on Tegmark. It depends on the basic statistics of an infinite cosmos. Here is how the argument works. Assume the universe is spatially infinite, which is what flat geometry implies. Assume the laws of physics are the same everywhere, which is what we observe up to the limits of our measurements. Assume the matter density and the energy density and the basic ingredients of the cosmos are roughly the same everywhere, which is what the cosmological principle tells us. And assume that within any given volume of space, there are only a finite number of possible arrangements of matter, because there are only a finite number of quantum states that any region of finite size can be in. That last assumption is the key. The universe is, at the deepest level, quantum mechanical, and quantum mechanics tells us that any finite region of space contains a finite amount of information. The number of possible configurations of all the particles within a given volume, including all their positions, momenta, and quantum states, is enormous, but it is finite. There is some maximum number of distinct microscopic states that a region the size of, say, an observable universe could be in. If the universe is infinite, then there are infinitely many regions the size of an observable universe. Each region is in some configuration. There are only finitely many possible configurations. By the simplest argument in probability theory, configurations have to repeat. Eventually, somewhere out there, there is a region that is in exactly the same configuration as ours, same galaxies, same planets, same atoms, same arrangements of neurons, same person sitting in the same chair, listening to the same words. How far away is the nearest copy? Tegmark and others have estimated, using the maximum information content of a Hubble volume, that the nearest exact duplicate of our region of the universe is approximately 10 to the power of 10 to the 29th meters away. That number is not a typo. It is 10 raised to a power that is itself 10, followed by 29 zeros. There is no way to write it out. There is no way to picture it. It is a number so large that it dwarfs the observable universe by factors that themselves dwarf the observable universe. But if space is truly infinite, that is the order of magnitude at which exact duplications begin. This is what cosmologists call the Tegmark Level 1 multiverse. It is not the multiverse of parallel dimensions or alternate quantum branches. It is just the implication of an infinite, statistically uniform space. If the universe is big enough and uniform enough and follows the same laws everywhere, then everything that can happen happens, and happens infinitely many times. Every possible person exists somewhere. Every possible arrangement of matter exists somewhere. The universe, if it is infinite, contains every story it could tell, repeated forever in different locations. This argument relies on what physicists call the ergodic property. An ergodic system is one in which, given enough time or enough space, every possible state gets visited. The universe, on cosmic scales, is thought to be ergodic. The matter is mixed enough, the laws are uniform enough, the variations are small enough that you can treat the cosmos statistically, and the statistical conclusion is that everything happens somewhere. This is also where inflation comes in. The theory of cosmic inflation, which posits a period of exponential expansion in the very early universe, does not just explain why the cosmos looks so smooth and so flat. It also tends to produce, naturally, a universe that is much, much larger than the part we can observe. In most inflationary models, the universe extends far beyond our observable horizon, and the matter distribution on the largest scales is statistically uniform. Inflation predicts a universe with the right properties for the duplication argument to work. So, if all of that is right, if the universe is infinite, if the laws are uniform, if quantum mechanics limits the number of possible states, then the question of where you are in the cosmos becomes very strange. Because there are infinitely many of you, each at a different location, each living a slightly different version of your life, or perhaps in some cases exactly the same version. The notion of personal uniqueness, of being singular in the cosmos, dissolves. You become, in some sense, a pattern that the universe is repeating infinitely in different places. The central thread keeps insisting on its point. When space has no edge, when geometry refuses to draw a boundary, then horizons become the only meaningful boundaries left. The infinite universe does not need an edge. It does not need a wall. It just needs observers, each with their own causal pocket, each at the center of their own finite sphere of visibility and reachability. The infinite universe is, in a sense, an infinite collection of observer-centered pockets, each with its own version of everything. The boundaries between them are not walls. They are the natural limits of what each observer can see and reach. This is also where infinity replaces the need for an edge in a deeper way. The intuitive question, what is at the edge of the universe, presupposes that the universe is a thing with a boundary. But if the universe is infinite, there is no boundary, and the question loses its grip. There is no edge, because there is no end. There are only horizons, and the horizons are local features of observers, not global features of the cosmos. The universe just keeps going, and going, and going, with every possible variation playing out in every possible region, forever. What this does to identity philosophically is hard to fully absorb. If there is another you, somewhere, doing exactly what you are doing, are you really unique? If there are infinitely many copies of every conscious being, every conversation, every decision, then the sense in which any single instance is special starts to feel attenuated. The Buddhist tradition, in its more contemplative forms, has wrestled with versions of this question for thousands of years. The cosmological version is, in some ways, more vertiginous, because it is not a meditation, it is a prediction. Of course, all of this depends on the universe being infinite, or at least so vast that the duplication conditions are met. If the universe is finite, even mildly so, the argument changes. There might be a maximum size beyond which copies do not exist, because there is not enough volume to host them. The closed universe possibility we discussed earlier, if it turns out to be correct, would change this picture. We do not know, with absolute certainty, that the universe is infinite. We only know that it looks infinite to the limits of our measurements. But whether or not the duplication is real, the central reality persists. The edge of the universe is not a wall. The edge is a horizon. The horizon is centered on the observer, and the observer is finite, even in an infinite universe. The infinity of the cosmos does not save you from your horizon. It just gives the horizon something endless to be embedded in. Which leads us to the last frontier, because so far, every edge we have examined has dissolved into something else. The particle horizon is a clock, not a wall. The event horizon is a shrinking causal sphere, not a barrier you can fly to. The geometry of space refuses to give you a boundary. The infinity of an infinite universe replaces the need for an edge entirely. So is there any edge that is real? Is there any wall, anywhere, in any framework physicists take seriously, that is a genuine boundary, not just another horizon? There is one possibility, one last candidate. And it is the strangest of them all, because if it is real, it is not the edge of space, it is the edge of physics. Part 10. The bubble wall, a real edge. There is one model in modern cosmology in which a true edge might actually exist. It comes out of the theory of eternal inflation, and it suggests that our entire observable universe, every galaxy we can see, every photon we can detect, every horizon we have been discussing, is sitting inside a bubble, and the bubble has a wall. Eternal inflation is a refinement of the basic theory of cosmic inflation, which itself was proposed in the early 1980s by Alan Guth and others to explain why the universe is so smooth and flat on large scales. The basic idea of inflation is that, in the very early universe, there was a brief period during which space expanded exponentially fast, doubling and redoubling in size in tiny fractions of a second, driven by a high-energy field that filled all of space. This expansion stretched any initial irregularities to such enormous scales that they became invisible, leaving the cosmos we see today, which is uniform on its largest scales, because it was once a tiny region that got blown up to enormous size. Eternal inflation extends this idea by noting that, in many models, inflation does not stop everywhere at once. Inflation is driven by a quantum field, and quantum fields have fluctuations. In some regions, the field decays out of its high-energy state and inflation ends, producing what looks, locally, like a normal universe with normal physics. But in other regions, the field keeps fluctuating, keeps inflating, and never decays. The result is a vast, ever-expanding background in which inflation is perpetual, and within which bubbles occasionally form where the field has decayed and produced pockets of normal universe like ours. In this picture, Our entire observable universe is one such bubble. We are sitting inside a region where inflation ended, and the surrounding eternally inflating background is so far away, expanding so fast that we cannot detect it. We see only the inside of our own bubble, which appears to us as the entire universe. From within, our bubble looks infinite, because the geometry of bubble formation in eternal inflation produces interiors that have an infinite proper time. To anyone inside, the bubble universe is endless. There is no inside the bubble experience of being in a finite region. The finiteness is only visible from outside. The wall of the bubble is the boundary between our universe and the surrounding eternally inflating background. It is a real physical surface, in the sense that on one side of it the field has decayed and produced a normal universe, and on the other side the field has not decayed and inflation is still happening. The two regions have different physics, in a sense. They have different field configurations. The bubble wall is the place where the field transitions from one state to the other. This is the closest thing to a true edge that any reasonable physical theory predicts. It is not an edge of space, exactly. It is more like an edge of phase. It is the boundary between two different states of matter, two different vacuum configurations, two different versions of physics. And here is the part that should make your jaw drop. In the theory of eternal inflation, especially when combined with the string theory landscape, the different bubbles can have different physical constants. The values of fundamental parameters, like the strength of gravity, or the mass of the electron, or the cosmological constant, are determined by which vacuum state the field decayed into. Different bubbles, formed by decays into different vacuum states, can have wildly different values for these parameters. Some bubbles might have stars and galaxies and chemistry like ours. Others might have no stable atoms at all. Others might have fundamentally different particle physics. The string theory landscape predicts, by some estimates, on the order of 10 to the 500th distinct vacuum states, each with its own set of physical constants. That is more than the number of atoms in the observable universe by an unfathomable margin. If we crossed the wall of our bubble, we would not just be entering a new region of space. We would be entering a region where the laws of physics might be different. The constants of nature might be different. The very particles that exist might be different. There is a real sense in which the bubble wall is the boundary between the universe we know and a universe that is not the universe at all, but a different one with different rules. Now here is the part where the central thread tightens around this idea. The bubble wall, even though it might be a genuine physical edge, is not something we can ever reach. The reason is that the eternally inflating background outside the bubble is expanding faster than the bubble wall is moving. From inside our bubble, the wall is receding from us at nearly the speed of light. The expansion of space inside the bubble is not enough to catch up with the inflation outside. So even though the wall exists, even though it is a real boundary, it behaves, for us, exactly like a horizon. We cannot reach it. We cannot even see it in any direct sense, because it is so far away and receding so fast that no signal from it could overcome the expansion of the space between us. So the only candidate for a true edge of the universe, the only model in which there is something like an actual boundary with another regime of physics on the other side, gives us a wall that is, in practical terms, indistinguishable from a horizon. It cannot be reached. It cannot be touched. It cannot be examined directly. The bubble universe model preserves the central pattern. Even when there is a wall, the wall behaves like a horizon, and the horizon is, once again, defined by the observer's relationship to the larger structure. This is what the central thread has been telling us all along. There is no edge that you can stand on. There is no boundary that you can reach. Even the most exotic models, where a real wall might exist in some sense, return us to the same conclusion. The wall recedes. The wall is unreachable. The wall is a horizon, however different its underlying physics might be. But there is one more twist to this story, one more avenue of investigation that some physicists have been quietly pursuing for decades. If our bubble exists in a multiverse of bubbles, then, in principle, our bubble could collide with another bubble somewhere in its history. Bubble collisions, in eternal inflation, would leave traces. Specifically, they would imprint distinctive patterns on the cosmic microwave background, patterns that we could, in principle, detect. So has anybody seen anything that could be a bubble collision? Has the edge of our universe ever, in some indirect way, already touched us? Part 11. Has the edge already touched us? There are anomalies in the cosmic microwave background that some physicists have, over the years, suggested might be evidence of a bubble collision. The most famous of these is the cold spot. The cold spot is a region of sky in the southern hemisphere, in the constellation Eridanus, where the cosmic microwave background is unusually cold. The temperature in that patch is about 70 microkelvin, colder than the average, which sounds tiny, but is statistically unusual given what we know about the typical fluctuations of the cosmic microwave background. It was first noticed in WMAP data and confirmed by the Planck satellite. It is real. It is there. The question is what causes it. The mainstream explanation is that the cold spot corresponds to a supervoid, an unusually large region of space with a lower than average density of matter. When light passes through a supervoid, it experiences a slight cooling effect due to a phenomenon called the integrated Sachs-Wolf effect, where photons climbing out of a region whose gravitational potential is changing lose a small amount of energy. A large enough void could explain the cold spot, although there is some debate about whether any of the candidate voids that have been observed are large enough to fully account for the temperature drop. The more speculative explanation, and the one that connects to our story, is that the cold spot is the imprint of a collision between our bubble universe and another bubble in the eternally inflating background. If two bubbles collided sometime early in the history of our universe, the collision would have produced a distinctive disturbance, possibly a circular cold or hot region in the cosmic microwave background, and possibly with specific patterns that could distinguish it from ordinary supervoid effects. A research group led by Stephen Feeney, working with collaborators including Hiranya Piris and Matthew Johnson, has spent years searching the cosmic microwave background for signatures of bubble collisions. Their analyses have placed limits on how many such collisions could have occurred in our past, and have not, to date, produced any confirmed detections. The cold spot remains, in mainstream interpretation, most likely a supervoid effect, rather than evidence of contact with another universe. But the search has not ended. Other anomalies have been proposed, including patterns of large-scale alignment in the cosmic microwave background, dipole asymmetries, and observations like the so-called dark flow, identified by Alexander Kashlinsky and collaborators, which suggested that distant galaxy clusters might be moving in a coherent direction in a way that could indicate large-scale structure beyond our observable universe pulling on us. More recent analyses have called the dark flow result into question, with subsequent measurements not confirming the original signal at the same significance. There is also an ongoing investigation into dipole anomalies in the distribution of distant quasars, with work by Nathan Seacrest and collaborators in 2021 and beyond, suggesting that the distribution of quasars on the sky shows an unexpected asymmetry that might not be fully explained by our motion through the cosmic microwave. Background. Whether this hints at something deeper, or is a systematic artifact of how quasars are catalogued, is still being debated. None of these anomalies has been confirmed as evidence of anything beyond our universe. The search continues, the data accumulates, and the limits on what we can detect get tighter. But the central thread is what matters here. If any of these anomalies turns out, against the odds, to be real, what they would represent is not the discovery of a wall we could cross. They would represent the indirect detection of horizons, of relationships between our universe and other regions that we can sense statistically but cannot ever directly visit. The edge, even in this most speculative form, remains untouchable. It is a horizon, not a frontier. So we have come, now, to the end of our cosmic tour. We have visited every edge the universe seems to offer. The visible boundary at 46.5 billion light-years, which turned out to be a clock, not a wall. The reachable boundary at 16.5 billion light-years, which turned out to be a shrinking sphere of causal influence centered on the observer. The geometry of space, which refuses to give us a boundary in any conventional sense. The bubble wall of eternal inflation, which is a real boundary in some sense, but functions, for us, as a horizon we cannot cross. And the anomalies in the cosmic microwave background, which might or might not be the faint signatures of contact with realities beyond our own. At every stop, we have been forced back to the same observation. The universe does not have an edge in the sense the intuition wants. It has horizons, and the horizons are not features of the universe. They are features of us, of where we are, of when we are looking, of what relationships our finite presence in this cosmos permits. Which means the question we started with, the question of where the edge of the universe is, has been quietly transformed into a different question. Not where the edge is, but who the edge is around. And the answer, the actual answer, is the one that has been hiding under everything we have been discussing this entire time. It is the answer that turns the cosmos inside out. It is the answer that makes the boundary of everything personal in a way that no astronomer would have predicted a century ago. The edge of the universe is not somewhere out there. It is somewhere very, very close to home. Part 12. The final inversion, the edge around you. The edge you were looking for was never a place. It was a limit on what you can ever touch. We started this story with the most natural question in the world, the question that has nagged at human minds since people first started looking at the sky. Where does the universe end? What is at the edge? What lies beyond? And we have spent every part since then watching that question come apart in our hands. The visible boundary turned out to be a clock. The reachable boundary turned out to be a shrinking sphere centered on us. The shape of space refuses to give us a wall. The infinity of the cosmos, if it is real, replaces the need for an edge with the strangeness of everything happening everywhere forever. The bubble wall of eternal inflation, the only candidate for a true edge, behaves like a horizon and cannot be crossed. So the four edges are not really edges. They are not walls. They are not boundaries you can reach by going far enough. They are conditions defined by relationships, anchored to observers, varying with where you are and when you are asking. There is no map of the universe with an edge marked on it, because the edge is not on the map. The edge is on the cartographer. Let me lay them out one more time, side by side, because the symmetry of this collapse is almost the whole story. The particle horizon, at 46.5 billion light-years, defines what you can see. It is the edge of your visibility. The cosmic event horizon, at 16.5 billion light-years, defines what you can reach. It is the edge of your causal influence. The geometric structure of space, whatever shape it has, defines whether the cosmos is finite or infinite, but does not produce an edge in either case. And the bubble wall, if it exists, defines a boundary between physics regimes, but it sits at infinite proper distance from us as far as we can ever practically reach. None of these is a wall. All of them are observer-centric. All of them collapse into the same realization. The cosmos does not enclose itself in a boundary. The cosmos is everywhere, and it is bounded only relative to where you are sitting in it. And of these four, only one is operational. Only one is meaningful in the sense that it actually constrains what you can do. The cosmic event horizon, the boundary at 16.5 billion light-years. That is the real edge. That is the line beyond which nothing you do today can ever propagate. Anything inside that sphere is part of your possible universe, the universe you can in principle affect. Anything outside it is forever beyond your reach. You cannot send a message there. You cannot send a probe there. You cannot influence it in any way. That sphere is your causal pocket. That sphere is, in the most rigorous sense, your universe. And here is the inversion that the entire story has been building toward. That sphere is centered on you, not on the Milky Way, not on Earth, not on humanity, on you, right where you are sitting, right now, listening to this. There is a sphere of about 16.5 billion light-years in radius drawn around you, defining the region of the cosmos you can ever causally interact with. That sphere is yours. It moves with you. It travels with you. If you walked across the room, it would walk with you, displaced by the same few meters. If you flew to Mars, it would fly with you. If you took a warp drive to the edge of the visible universe, it would go with you. Still 16.5 billion light-years in radius, still centered on you in your new location. You are at the center of your universe, not metaphorically, not poetically, operationally, in the strictest physical sense. The cosmos has a boundary, and the boundary is drawn around you, and you cannot escape being its center, because the center moves with the observer. I have a friend at the other end of the country. She has her own sphere centered on her. Her sphere overlaps with mine in most places, but it is offset by the few thousand kilometers between us. There are regions of the cosmos that are inside my sphere and outside hers. There are regions that are inside hers and outside mine. We share most of our universe, but not all of it. And every other person on the planet has their own sphere, and the spheres overlap and intersect and share most of their volume, but each is centered on a different observer. This is what I mean when I say the edge is around you, not around the universe. There is no single edge of the universe that everyone agrees on. There are billions of edges, one for every observer, each centered on its respective observer, each moving with its observer, each defining the personal causal pocket of that observer. The cosmos is a vast, structured, complex thing, and yet, from the standpoint of what is reachable, what is interactable, what is real in the sense of admitting any influence from you, the cosmos is your sphere, and only your sphere, and the rest is just scenery you cannot touch. And this sphere is shrinking. That is the cruelest and most important fact of all. The accelerating expansion of space, driven by dark energy, is gradually contracting the radius of the cosmic event horizon in proper distance. Year by year, the sphere is closing in. Galaxies that were inside the sphere a billion years ago are now outside it. Galaxies that are inside it today will eventually slip outside. The pocket is shrinking, slowly, inexorably, and there is nothing anyone can do to stop it. In the very long run, in roughly 100 billion years, the sphere will have contracted so much that almost nothing will remain inside it except the local group of galaxies, gravitationally bound and therefore moving with us against the expansion. The Milky Way and Andromeda will have merged. The other members of the local group will be there too, all clinging to each other against the cosmic tide, and outside, the sphere will be empty. The rest of the universe will have crossed out, beyond reach, beyond signal, beyond any possible interaction. Future observers, our distant descendants, if there are any, will look out at the night sky and see only their own galaxy and a few neighbors, in a void that goes on forever, as far as anything they can detect. They will be alone in their pocket of the cosmos, which by then will have shrunk down to a single galactic island. This is the island universe scenario, and it is the projected fate of every observer in an accelerating cosmos. Each observer, in the long run, becomes confined to their own causal pocket, their own personal universe, surrounded by darkness. The edge of the universe will, by then, be quite close. It will have closed almost all the way in. The boundary of what you can affect will be just outside the local group. Beyond that, nothing. The edge will have arrived at your doorstep, still centered on you, still moving with you, but with almost everything that used to be inside it now sitting on the other side of an unreachable line. There is a deeper layer to this picture, still, and it touches on the holographic nature of horizons. In black hole physics, every horizon has an associated entropy given by its surface area divided by 4 times the Planck length squared. The cosmic event horizon, the one we have been discussing, is no exception. It has an entropy. It has a finite information capacity. The horizon, in this view, is not just a boundary of causal influence. It is a kind of information boundary, a surface that encodes everything we can ever know or affect. Some physicists have suggested that the universe, on the largest scale, behaves like a hologram, with the information in the bulk of space being equivalent to information stored on the boundary. If that is right, then the cosmic event horizon, your horizon, the one drawn around you, is, in some sense, a complete description of your universe. Everything you can ever interact with, everything that matters for you, can be encoded on that surface. The universe is, in this picture, a hologram drawn on the inside of your horizon, and that horizon, again, is centered on you. So what is the universe bounded around if every observer is at the center? The answer is everyone. The universe is bounded around every observer, all at once, in slightly different ways, with slightly different boundaries, all overlapping, all interlocked, all moving with their respective observers. There is no single boundary. There is a vast network of boundaries, one for every observer, each personal, each unique, each centered on its observer. The cosmos is, in this sense, the union of all these personal universes, each defined by the limits of what its observer can ever touch. This is a profoundly strange way to think about the cosmos. And it is, as far as we can tell, the way the cosmos actually works. The universe is not an object with a single boundary. It is a relational structure in which every observer carries their own boundary with them, and the boundaries do not match. Your universe is yours. Mine is mine. They overlap, but they are not the same. We share most of the same cosmic neighborhood, but the limits of what each of us can causally affect are different, by tiny amounts, because we are in different places. The closing line, the one that has been forming under everything we have said in the last several hours, is the one that ought to stay with you. The edge you were looking for was never a place. It was a limit on what you can ever touch. It is not a wall in the sky. It is a sphere around you, defined by the relationship between your finite presence in the cosmos and the geometry of expanding space. It is centered on you because the laws of physics center it on you. It moves with you because horizons are observer-dependent. It is shrinking because the universe is accelerating, and in the very long run, it will close in around you and your nearest neighbors, leaving you on a small island of mattering, surrounded by an unreachable everything else. The question of where the edge of the universe is dissolves, in the end, into a different question entirely. Not where, but who. Not what is at the boundary, but whose boundary. The cosmos is not bounded around itself. It is bounded around each of us. And each of us, sitting somewhere in this enormous structure, is the center of a finite sphere of reach, embedded in a possibly infinite space, watching most of that space slowly drift beyond what we can ever influence. There is something almost intimate about this. The universe is not impersonal in the way the high school science textbook suggested. It is not a vast, indifferent expanse with us as a tiny, irrelevant speck. It is a vast structure, yes, but it is structured around observers. The boundaries it draws are personal. The horizons it produces are local. The edge it has, if you want to call it an edge, is the edge of you. It is the edge of what your finite existence can ever reach into. And the mystery, in the end, is not solved. It is deepened. We have answered, in a sense, the question we started with. The edge of the universe is not a wall. It is a horizon. It is centered on you. It is shrinking, We have details. We have numbers. We have explanations for every aspect of it. And yet, the question of why the universe is structured this way, why physics produces observer-centered horizons, why the cosmos is built such that every conscious thing is the center of its own bounded reachable region, that question remains open. Some physicists think the answer lies in holography, in the deep relationship between information and gravity. Some think it lies in the structure of quantum mechanics itself. Some think it is just a brute fact of how space-time is made. The question dissolves. The mystery deepens. The universe, on close examination, turns out to be far more personal, far more relational, far stranger than the intuitive picture of a wall at the end of space. There is no wall. There is no end. There is only a horizon drawn around each of us, shrinking with the cosmic acceleration, defining the sphere of what we can ever touch. And inside that sphere, for as long as we have it, is everything that will ever matter for us. Inside that sphere is our entire universe, in the only sense of universe that has any operational meaning. The edge of the universe is around you. It is centered on you. It is yours. Nobody else has the same one, and it is closing. That is what happens at the edge of the universe. The edge happens to you. The edge is you. The edge has been you all along.